ever. You know, I don't even care that the rest of the rocket's there. Just like throw a computer into space. How does a rocket think? We're gonna learn about that. Okay. How does a rocket know when to deploy parachutes? How can we communicate with the rocket? How does a rocket know and remember its altitude? So avionics is what I've been throwing around. It's aviation plus electronics. This is a term broadly applied across aerospace. So you see those people on the left working on a Mars rover or something. That's avionics. On the space station, we call space station stuff avionics. Anything that flies goes to space, avionics. Also airplanes. So you'll hear that in the airplane world too. So a computer that does all those jobs, right? Letting us talk to the rocket, launching parachutes. That sounds pretty complicated for a computer to do. But it's really a very simple system. So let's think about what we need it to do. Oh, actually, I'll let you guys help me with it. Based on what I just said, what are some things the computer needs to do?
Think.
More specifically.
Ignite the EMATch.
Ignite the EMATch, good. Record the altitude, excellent. Deploy parachute, okay. Know when it's apogee, yes. It needs to know when it's reached its peak. That's an important step. Go to Orlando first.
Communicate.
Communicate with the team, yeah.
Starts the motor.
No, not in our team. That can happen, but not in our team. Mister, I can tell you know your stuff back there. Okay, anything else? I think we got most of them. All right, I think we got pretty much all these. Deploy parachutes only at the correct height. Record the highest point that the rocket reaches. Track the rocket's location so that we can find it later. Oh, we forgot about that. We need to track where our rocket is, because if it's flying off into the desert, it'd be really useful if we had like a GPS coordinate for it. We needed to set off the charges to deploy the parachutes, and we need it to send performance information to us while it's flying. So I think we got all those things. Okay, so I've broken this down in a way where it kind of categorizes by functionality. So these 2 points indicate that we need to know the height of the rocket at all times. How would we do that? That seems kind of complicated. It's actually not. So when we travel up, pressure scales with altitude. You might not have known this, but you know, well, probably you know that if you go to like Denver and you play football, your football is going to transfer a little bit farther. That's why kickers love Denver. But it goes all the way up into space that this pressure scales on this known curve. So at 10,000 feet, our pressure is about 70 kilopascals. At 30,000, 30 kilopascals. We can use this to determine what height we're at. It's very well documented. So how do we measure pressure? Do we need to devise some kind of system to do this ourselves? Do we need to be at the lab till 2:30 in the morning every day, soldering, putting in wires? No. We live in an age of microchip computers where we can order this from China for like $5. So this is something that you could buy online. It's a typical microelectronics pressure sensor. So these models I'm going to show you on the screen for this example is stuff you would do if you're interfacing with like an Arduino or a Raspberry Pi. Once you get into like professional flight computer development, we're going to get into how you do that on a PCB. Not in depth because I'm no expert on that, but if you want to do it just yourself, play around with a Arduino with it, it would look something like that. These little dudes on the top, this is the actual sensor. This is the thing that measures your pressure. So what do we have so far? Boot camp's flight computer. We have a pressure sensor. By the end of this slide, we're going to have a full flight computer. Well, not at the end of this slide, but the end of this presentation. And some of you who are electrical engineers are going to scream at me, or people who know stuff about electronics are going to be very angry with some of the gross assumptions I make. But remember that this is for the general audience, describing the broad functionalities of how a flight computer works. Okay. What else do we need to do? We need a GPS if we're going to track the rocket's location and find it later. Well, check it out. This thing we can buy online. Look, it's a GPS module. We don't need to do anything other than get this little piece here, stick it on our computer. We needed to set off charges and deploy parachutes equals we need to send a strong current on command. Why a current? Remember I talked about E-matches? Electronic matches. These things work on sending a current through this wire, burns a little filament, and ignites the rest of the black powder around it. So, like I said, we need current and a strong current. We can use a electronic relay for that. So this is a piece that sets off a signal only at a time designated by the computer. Another gross oversimplification. Don't yell at me. It needs to send performance information to us while the rocket is flying equals we need an antenna and a way to transmit radio frequencies. So I'm just going to stick an antenna on there. Of course, we need to generate the signal. I'm not going to talk about that. Yes, our antenna is literally just a simple wire. So if you look at the flight computer, there's just like a little dangly wire on the end. You might be like, why is this stupid wire here? It might fall off, which has fallen off like 5 times. It's an antenna. Okay, some extra magic. We need a battery so that everything has power, right? Pretty self-explanatory. We need a memory storage device to save the data and to save software on it. So there's a micro SD card. We don't use that, but it's an example. We need an actual microprocessor so it can process code. Looks something like that. Also, again, you can buy it online for like 30 cents. Add an operating system and software, so that's something you develop as a person creating this from scratch. How it actually takes in all these inputs, makes its decision. So all the code, that's all software based. And if you know what you're doing and you're a proper electrical engineer, not like me, who's a hobbyist electrical engineer, you can put this all on a PCB so that's all tidy. So we have all these pieces. We're gonna get our electrical engineering fairy godmother. Hey, look at that, we have a flight computer, woo! So this is the telemetrum. It is a COTS flight computer. What's COTS? What? Commercial off the shelf. So that means we bought it from somebody. This is from Bdale Garby. He's a dude. If you email his email, he'll be like, oh yeah, like he'll answer your questions about it. It's just like a dude making flight computers. It's really cool. So what are the pieces on here that we recognize? Well, check it out. What's this? Do we recognize that? I heard it over here.
The GPS.
The GPS, yes, GPS. Oh, there's buttons on here I've just discovered. Okay, GPS. Cause look, let's go back. Let's go back a tad. GPS, look, that same antenna thing. This is a antenna for the GPS satellites. It's the same thing. Look, it's there. This little thing right here. This is our pressure sensor. Remember we had that tube? That's what this is. All this junk on the back, this is all, so remember those sensors were attached to like little chips. Imagine you take all the components off of there, because it's really just wires, resistors, chips. You put that all on a PCB, print it out, and have it shipped to you. That's all that stuff on the back, just doing the processing for each sensor, doing the microprocessing to run the code in the operating system. All the circuitry needed to generate radio frequency signals. Our antenna would be like right here, right? Not curved like that, but yeah. All that's just printed on the back. We know all the pieces, the crucial pieces at least, of how this works. Of course, we need a battery. Any questions on that yet? Any confusions? No? So you all can build a flight computer like right now? This is, of course, a simplification. A few things I glossed over. So there's another piece on there called accelerometers. So this is a sensor that helps us to detect acceleration. So the fancy flight computers, when a rocket launches, it sees there's a big acceleration. It's like, okay, the rocket's launched. I will go into I'm flying mode and start recording data. Same way with if it sees a sudden jolt, it can detect that that's a parachute going off. So it can send us data, your main has just come out, your drogue has just come out because it's felt a sudden acceleration on it. So they're very useful for that. Terminals, this is how you connect the deployment charges to the flight computer. They're just little screw things on the end, you stick the wires in, how you get to the charges. I've glossed over electrical engineering as a whole, so just keep that in mind. and how the software works in the interface that the user sees. So there's a lot that I didn't cover, but with what I did, you will be able to explain to your friend what does a rocket flight computer need? What is specific about a rocket flight computer that it needs to operate and how it works? Okay? Avionics, you'll probably learn more later. Okay, is there any questions? It's a lot of information, please ask me. Okay, so installing a flight computer, we covered this a little bit before in our internal structures slides. So usually the flight computers are mounted on like a little board, put on some rails like this. So you can see examples here. You've got your bulkheads on the end and your flight computer is mounted on a little tray on the inside. And there's Raj and Joe working on the avionics at competition last year right there. And look at that, them sealing it up and getting ready to put inside the rocket. And it goes in just like that. Okay. All right, deployment charges go on the bulkhead. A little redundant, we've covered this. Remember, it passes through the bulkhead, goes to these terminals. These terminals have an e-mesh that goes into the black powder. Okay. Talking to the rocket, we haven't covered this. So while the rocket is flying, the team can view live data. Remember that antenna we had? This data is streamed on the 70 centimeter ham radio band from the flight computer. Remember, also I mentioned this would come up again. Ham radio, it is a civilian series of radio frequencies that civilians can get licenses to use. So it's not like a radio station that would play music. That's slightly different. That's like for commercial music purposes. If you wanted to talk to your friend, or you can even talk to the ISS, you can get on these ham radio bands, which are reserved by the government for just civilian use. And you can talk to whoever you'd like, other than you need a license. That's really cool. It's a reserved way, you know, if ever a catastrophic thing happens, all cell phone communication is down, you know, you could still, if you had a radio, talk to people. It's commonly used in emergencies like hurricanes and stuff like that too. Yeah, you must have a ham radio license to transmit on this frequency. Here we have Ravi demonstrating our Yagi antenna we use to talk to the rocket. So that's literally the thing we point at the rocket as it's flying, and it talks to us on that antenna. Okay, so as that data comes into the antenna, it goes into a GUI, or graphic user interface. So this was all developed by this guy, Vito Garbi, I talked about, who makes the telemetrum. He programmed all this. It's all software that feeds into here. And it's going to give us all this data live as the rocket is flying. So on here you can actually see my call sign. That's my ham radio call sign. You can see the current height of the rocket. You can see the current speed of the rocket. You can see how fast its maximum was. It's going to give you all this data as it's flying. And it's really great. You can tell exactly what's happening as it's in the air. And I have a little video about that. And again, because this is long, I'm going to skip around. This is a pressure test they did. So this was not a real flight that happened. We have a pressure chamber in one of the labs that we use. We're actually required by competition to use to prove that our flight computers are functioning before we fly them in a rocket. So basically lower the pressure to the pressure we expect at 30,000 feet. Make sure that our computer behaves nominally. Alright, so this is its idle screen. You can see it's recognized it's on the pad right now. So if you look at the top, it says state, pad.
Listening to summary, but we're going
Like learning, which is probably.
Okay, pad. Whoop, back up.
2, 1.
So I flipped on the pressure chamber. That's it chugging in the background. It's really old. So now it's in boost because it sees that pressure decreasing. It thinks it's going up in the air. Really, it's just in this little chamber. But remember, all it's sensing for altitude is pressure. And it's chugging. That's gonna die, sort of. Like, so there's this professor named Dr. Bering who lets us use his pressure chamber, and I think the pressure chamber was born the same year he was, and he's very old. So now I've stopped the pressure. It sees that the drogue has come out, so it's telling us it's flying under the drogue parachute. It's telling us the speed, and check it out, is negative because it's going down in altitude right now.
Which is great. So it's an unusual response.
And I'll skip around because it's slow. Aha, and then we got main. So it got to, oh, let me back up. So we told our flight computer before we flew that we wanted our main to come out at 1,000 feet above the ground. So you see height is going slowly down to 1,000 feet. So we expect it to stay in main as soon as we get to 1,000 feet.
So we're about to reach 1,000 feet here in a second.
So another thing we use to test to make sure that's all working, so we have the radio signal, but that doesn't necessarily mean that the terminal is working, so we put little lights at the end of the terminal. So when the light, the LED lights up, that means there's a current running through it. That current would be going straight to the E-match, igniting our black powder. So we have two checks, radio signal and a little light that lights up when current is going through it.